Everybody have a good Halloween. Good Halloween? Okay, that's good. That's good. Good Halloween weekend. All right. So let's return to our topic last time. We just finished last time talking about the different small signal models, and I've explained to you guys about the hybrid pi and the T model, either of which one you can use in the problems. But let's talk about one last topic that matters with MOSFETs, and that is the body effect. Now, so far when we've been looking at MOSFETs and we've talked about the simple amplifier circuit that we analyzed last time, we've always been assuming the source and the bulk are connected together. What happens if the source and the bulk are not connected to each other? How does that affect the small signal model? And I do want to talk about that because it does turn out that in MOSFET's designs, it has an effect. So if we think about just a simple diagram, and let me kind of redraw this before. So here is our bulk, and just drawing a quick sketch of an MOSFET, let me do that, fill that in. So here is our transistor in saturation. So we're in pinch off. So here is our N plus regions, here's source, here's our drain, and here's our p-type bulk. Okay, so as we recall last time, because we have N-type and p-type regions, there is a depletion region around this. So as with any situation where we have an N and a p-type region merging together, we're going to have the depletion region forming. And we talked about this last time when we were looking at how MOSFETs work. All right, now the source and the bulk regions, and for that matter, the drain and the bulk regions, need to be reverse biased. We cannot turn those diodes on because otherwise current's going to be flowing from the drain into the bulk or from the source into the bulk. And then the MOSFET quits working. So under normal circumstances, the bulk and the source are at the very least zero biased or reverse biased. So the bulk source and the bulk drain junctions must be reverse biased or at the very least zero biased. And when we were looking at our three-terminal MOSFET before, we always had drain, gate, and we said source and bulk are connected together. So in this case, we're assuming a zero bias. The voltage across that source bulk junction is zero, which is off. That is, we basically treat that as reverse bias, anything less than or equal to 0 volts. So at the very least, we need to be this. However, it is possible for the source and the bulk to be at different potentials so long as the source-bulk junction remains reverse biased. So long as the junction is reverse biased, we can make those voltages different. And for the MOSFET, what that means is I can make the voltage at the source greater than or equal to the voltage at the bulk. It remains reverse biased. If I want to turn on that PN junction, the source would have to be more negative than the bulk. But it can certainly be more positive than the bulk and still maintain reverse bias. So for an MOSFET, Vs, the voltage at the source, can be greater than or equal to the voltage at the bulk. So kind of common sense if we want to preserve the operation. So what happens if we do this? If we make Vs greater than Vb, what will happen is the depletion region between the source and the bulk is going to get wider. We're making it more reverse biased. So recall how a PN junction works. As we increase the reverse bias, the depletion region widens. And in turn, as we widen this depletion region, we also tend to widen it around the channel that's near the source as well. So that depletion region is going to increase in width. As that happens, as we widen the depletion region, the channel gets squeezed. It gets compressed near the source end. So the channel gets squeezed. Now, as I squeeze the channel, as I make the cross-section of the channel smaller by making the depletion region wider, what do you think is going to happen to the drain current? Going to go up or going to go down? As I make that channel smaller. It's going to go down. And so, all else being the same, for the same value of VGS, I'm going to have less drain current. So for the same value of gate source voltage, if I make the source more positive than the bulk, I'm not going to have the same geometry on the channel. And I'm going to have less effective drain current as a result. All right? So there are lots of ways we can model this behavior, but we call this the body effect. Well, mathematically, how do we describe this behavior, the fact that the drain current goes down? Well, the way we do this mathematically is we characterize the body effect as effectively the same thing as a change in the threshold voltage. So in the DC equations, we are going to write an additional equation that describes how that threshold voltage can change. And here's the equation we use. This is the equation we use to model the body effect. So this is the zero bias threshold voltage. So when Vs is equal to Vb, that is the threshold voltage we have. In other words, that's the standard threshold voltage we're already familiar with. Then we have these other parameters. So we notice VSB, the voltage between the source and the bulk. Our other parameters, this is our body effect parameter. And the magnitude of this is typically on the order of about 0.4 to about 0.5 square root volts. Notice the units, square root of a volt. 2 phi f is our bulk potential. And the magnitude of 2 phi f is normally on the order of about 0.6 to 0.8 volts. In other words, kind of like the standard turn-on voltage for a diode. And then VTO is the zero bias value of the threshold voltage. So we notice if VSB is equal to 0, this term and this term cancel out, and so then it's just gamma times 0, VTO is equal to this times 0. All right? Now it turns out that we can, because of this body effect equation, it actually adds an additional term to the small signal diagram. GMB, G sub M and G sub MB in this case. So G sub M was transconductance. G sub MB is body transconductance. And we can write this as the change in the drain current with respect to a change in the bulk source voltage, assuming that VGS and VDS remain constant. Now, I'm not going to bother to try to calculate this or to do that derivative. It's kind of messy mathematically, but I'll show you the result. What we'll get is the following result, that GMB is equal to a factor times the standard transconductance. So G sub M for the transistor, we can multiply it times some factor and get GMB. And in this case, this will be equal to the following. And that is our multiplication factor. So this is our scaling factor. We can take the standard G sub m and multiply it times that scaling factor where we've got our phi sub f, our gamma, and we plug all the numbers in. And normally this is in the range of about 0.1 to 0.3. And for most modern processes, it's usually more on the lower end. As we have gone into smaller transistors and smaller feature sizes in transistors, normally that gets smaller, that parameter gets smaller. Well, because of this, turns out we can modify our small signal diagram, because if we move the source voltage, that will also affect the drain current as well as changing the gate voltage. And so our small signal model we get looks like this. So our equivalent small signal model, I'll just redraw this. So here's our standard small signal model we're already familiar with. And now I'm going to add a term to it. I'm going to add this. There's also a GMB multiplied times VBS, an additional dependent current source. And in this case, we treat the bulk as an additional input terminal. So in this case, we now have VBS. And so the body effect adds this small transconductance, additional transconductance, this additional voltage-controlled current source. But keep in mind, this is only a few percent of the value of this current. So the body effect is not significant under most normal circumstances. And since typically we are normally going to take transistors and just connect the source and the bulk together, it's not really that big of an issue. But if we do have circuits where for whatever reason we are separating the source and the bulk, and we're drawing this instead as a 4-terminal device, in this case, that is a small signal model you have to use. Now, I point this out because, surprisingly enough, it turns out that people have actually built amplifiers doing this. Normally, we're going to be building amplifiers this way, using that dependent current source. It is also possible, however, to build an amplifier circuit using that dependent current source. Now, you don't get as much transconductance, but there is a particular advantage to using your bulk as your input terminal, is you can build an amplifier that operates at a much lower minimum supply voltage. And so people have done very, very low power, low voltage designs using that body source transconductance in order to build very low voltage amplifiers. So it is not common, but it is not unheard of. So that's why I wanted to bring this up. Now, we're not normally, going to be dealing with the body effect. I don't think any of the homework problems really ask you much about the body effect. But I just wanted you guys to be aware about it, because in more advanced circuit designs, high-performance circuits, you will occasionally see body-driven amplifier circuits, where they are separating the bulk and the source terminals, and they're actually operating them as amplifiers. All right? Questions about this? So, neat concept. In fact, one of my colleagues when I was in graduate school and getting my PhD did his entire dissertation work on the design of these amplifiers. In fact, he did a lot of the pioneering work on the designs of these techniques. So, all right, so we've now covered the basics we need to go. Now let's start looking at some amplifier topologies. And these are the amplifier topologies you guys are seeing right now. You've been doing measurements for them in the lab this week. Let's talk about those and let's see how to analyze those. There are three basic amplifier configurations that can be constructed using a single transistor. The first is the common source amplifier. Or as you'll see it abbreviated, just CS, CS amplifier. So the common source amplifier is the topology we've looked at before. In its most basic form, you have a drain resistor, you ground the gate, and then you have an AC source combined with a DC source in order to provide biasing. So we've seen this before. In this case, the AC source is our input voltage. We take our output, V out at the drain of the transistor. So we've already looked at this. We've actually analyzed this simple amplifier circuit already. Now, this is an NMOS circuit, right? But there's no reason why I have to use an NMOS transistor. Well, anything I can do with an NMOS, I can do with a PMOS. How would I draw a simple single common source amplifier in that way? Well, let's do it. You do it like so. In this case, the source is connected directly to VDD. Your drain is grounded through a drain resistor. Once again, your output voltage is at the drain. Once again, you have an AC source combined with a DC source. I flip the transistor upside down. So here for the PMOS, source is VDD, drain resistance between drain and ground. What does that small signal diagram look like for the PMOS versus the NMOS? Looks the same. Because like I said, it's the same small signal model, and once you convert these to small signal and you take all the DC voltages and set them to 0, you're going to have the same topology for the small signal diagram. So anything I do with NMOS, I can do with PMOS. Now, I point this out because many times, guys, in the examples in class, I'm going to draw the NMOS version. But if you can do it in NMOS, you can do it in PMOS. You can always flip the topology upside down and replace the NFET with a PFET, and it will work just fine. Okay? That's our first topology. The second topology is the common gate amplifier. The difference between these two circuits and the circuits I'm about to draw is where you insert the AC input voltage. So here, once again, here's our NMOS version. Look what I've done here. I've simply separated the input, and now I'm putting it here going into the source. What am I doing here? In this circuit, I am changing the drain source voltage, pardon me, the gate source voltage, VGS, by wiggling the gate and grounding the source. In this circuit, I'm changing the gate source voltage by AC grounding the gate and then wiggling the source. So I'm getting the same kind of effect. It's just a matter of how I'm changing the gate source voltage. So again, I have an NMOS version and a PMOS version. So questions about this? Pretty straightforward. All right, what's our final topology? Yes? Excuse me.
Common gate and common source topology, like equivalent-ish?
Well, we're going to see just how equivalent they are. In some ways, they're very equivalent, but in other ways, they're significantly different. All right? The way to understand that is, of course, to do the small signal analysis, and we're coming to that next. I mean, that's the beauty of what you're trying to learn in this class, guys. You never have to look at a circuit and say, I wonder how that works. No, you're going to write the equations and learn how it works, figure out how it works. That's the whole point of why we're in this class, okay, where you can answer those questions yourself. Third topology. The common drain, or CD amplifier. You'll sometimes see this called the source follower. All right, how does that work? Well, that one's a bit different than these two. For the NMOS version, I connect the drain straight to VDD. But now I connect the source to ground through a source resistance. And then I take the output voltage at the source. And of course, I can do the same thing with PMOS. And so here we're taking the output not at the drain, but at the source. But the input is still at the gate. These are our three fundamental transistor topologies. They differ either in where we're injecting the input or where we're taking the output. All right? Now, there are other, what I would call, fundamental transistor topologies. In fact, there's one we're going to look at later called the differential amplifier, which people consider also to be a fundamental transistor topology. But that requires more than one transistor. In this case, we're assuming what's the minimum number of transistors you can get by with. Here we are. All right, so what we're going to do is we're going to learn how to do small signal analysis, and we're going to start by analyzing how these transistors work. Now again, usually when I do the analysis, I'm going to stick with the NMOS version, but you can do the PMOS version exactly the same way because you're going to see that the small signal diagram is going to have the same topology. All right, now before I start jumping into small signal diagrams, I want to first talk about why we are caring, what parameters we care about. And we actually mentioned this last time in the last lecture. Now, when we start looking at how amplifiers behave, there are three parameters we're going to care about. First of all, is small signal AC gain, right? What's V out over Vn? What's the output voltage versus the input voltage? The amplification factor. Well, obviously we care about that if we're building an amplifier. But there were two other parameters we talked about last time when we did our first simple example: input and output resistance. Actually, I'm going to call this R sub O. I'll stick with the nomenclature in the text. So we looked at small signal input resistance Rn and small signal output resistance Ro. And last time we looked at how to calculate this using Thevenin's theorem. But you know, there's always the question people ask about. Obviously, gain makes sense. We care about how much amplification factor an amplifier has. Why do we care about these? Why in the world do these matter? I mean, do we calculate the input and output resistance just because your professor wants to torment you, okay, and wants you to see if you know Thevenin's theorem? No, as it turns out, there's a very good reason why we care about input and output resistance, and let me do an example to illustrate this. Let's kind of think of this not with any specific amplifier, but let's think about this more of kind of a block diagram. So let's say we've got an amplifier. And there is some amplifier circuit in here. It can be any one of the topologies we talked about or some multi-transistor topology. Doesn't matter. But here's our amplifier. And when I connect this amplifier, I'm going to connect it to a source and to a load. So I'm going to say that my input circuit is a signal voltage in series with a signal resistance. Now, why did I drive it this way? What does a voltage source in series with a resistor represent from 2112? It's a Thevenin equivalent. Isn't this a Thevenin equivalent circuit? That's exactly what this is. This is a Thevenin equivalent circuit of something that's connected to the input of my amplifier. So this could be anything. I mean, it could be another amplifier, it could be some other type of circuit, but as long as it's a linear circuit, we know from Thevenin's theorem, we can always distill it down to a voltage source in series with a resistor. And that's exactly what we're going to do here. And then I'm going to connect the output of my amplifier to some load resistance. So again, I've got some equivalent load resistance, which once again we could model as a Thevenin equivalent resistance of something that I'm connecting my amplifier to. So I don't know what I'm connecting this amplifier to, speakers, the input of another amplifier, some other type of circuitry, whatever. As long as it's a linear circuit, I can calculate what the effective load is, the effective input resistance of that next stage. So here we start to see Thevenin's theorem being applied to the way we're looking at this. All right. What I'm going to do now is I'm going to replace that amplifier. I'm going to take this amplifier, and whatever this amplifier is, I'm going to turn it into a simplified model using basic circuit elements. So I'm going to model this amplifier. First, it's going to have its own input resistance. I'm just going to draw resistance. My amplifier circuit has an R sub n, a small signal input resistance. And I'm going to model the amplification behavior as a voltage-controlled voltage source. So in this case, this element here has a value of AVO times VI, where VI is the voltage across that input resistance. And then finally, this is connected to an output resistance R sub O, and then that connects to our load resistance. So what I just did here is I just replaced my amplifier circuit with this. Now I drew it this way in order to incorporate the input and output resistances. All right? AVO is going to model the voltage gain of the circuit, except in this case I'm just doing it just as a simplified voltage model, voltage controlled voltage source. Okay, so questions about this? Everybody see what I've done here, how I've drawn this? Okay, why did I draw it this way? Because now I'm going to take this circuit and I'm going to do some simple nodal analysis to it and write myself a few equations. So in this case, all right, let me go ahead and draw a current here. So I'm going to have a voltage V sub I and a current I sub I associated with the input of that amplifier. Rn will be equal to V sub I over I sub I, right? In other words, the small signal input resistance is going to be the small signal voltage divided by the small signal current flowing into the input of the amplifier. Should be fairly straightforward. What is R sub O? R sub O in this case is going to be equal to the output, or the effective resistance at the output when V sig is equal to 0. So in this case, I'm going to redraw this. Let me draw this over here. So I go back to my original circuit. And I set V sig equal to 0. So all I've got left is R sig. So in this case, once I do that, if I want to calculate the output resistance, here is my I sub x. I'm going to use the source driving technique. Here's V sub x. And then R sub O, in this case, will be equal to Vx over Ix when V sig is equal to 0. And that, of course, is the source driving technique we learned about, right? How do you calculate the input resistance or any input-output resistance? You zero out all the other sources in the circuit. That's exactly what I'm doing here. So this is the source driving methodology or technique. So that's where these numbers come from, right? I mean, that's how I'm calculating Rn and Ro, is by just using small signal analysis. And we'll be doing this as we go through and look at these other circuits. Okay. So given this, let's now go and let's write some equations. So note here, if I've got Vi here and this is ground, then this node is Vi at that input. Here, this voltage is AVO times Vi at that node because this voltage source defines that. And then I've got VO at the output. All right, so given this, let's write a few equations. What's Vi equal to? Let's look at Vi. What do I have there? Between V sig and Vi, I've got two resistors in series. What kind of circuit is that? Voltage divider, yeah. I mean, I could write a nodal equation, but I can also just write the voltage divider equation. So at the input node, I know this must be true. I mean, I could write the nodal equation at the Vi node. I'd get the same equation. Or Vi over V sig is equal to Rn over Rn plus R sig. So the ratio of Vi to V sig is simply Rn over Rn plus R sig, which incidentally has to be less than 1. What about VO? Well, once again in this case, what do I have? A voltage divider between RO and RL. And once again, I can write that. Where it's equal to RO over RL plus RO times AVO times VI. That's the input voltage to that divider. All right. Also, I'm going to define the following. AV, which is the voltage gain of this amplifier, is going to be equal to VO over VI, which in this case will therefore be equal to AVO times RL over RL plus RO. So in this case, once again, I'm just taking VI, dividing it out. What I've got left is here, and we're calling that AV for our amplifier. We note AVO is equal to VO over VI, provided that RL goes to infinity. So if I let RL go to infinity, infinity over infinity is equal to 1, and AV is equal to AVO. So in other words, AVO is just equal to this. We call this the unloaded gain. In other words, AVO is equal to AV if there's no load resistor, if R sub L is infinity. A no load condition. Yes?
Why is RL infinity when there's no load?
No, I'm simply saying if we set RL equal to infinity. That's what I'm saying, if we set the load to infinity.
So why is it called unloaded?
Because it has no load. If you take the resistance away, there's no load connected to it. So RL goes to infinity. Infinite gain means it's an open circuit. Or infinite resistance means it's an open circuit, right? So when RL goes to infinity, there is no load. It's an open circuit. So it's unloaded. All right? Well, given these definitions I just did here, I'm going to write an equation. I'm going to look at the global gain of this entire circuit, which is the output voltage divided by V sig, our signal voltage, not VI. It's going to be V sig, our source, our input source. So if I were to disconnect that source and measure the output voltage, I would see V sig. So the question I'm going to ask is, okay, what is VO over V sig? Well, that's equal to I'll use the chain rule. I can break this down and say it's equal to VI over V sig times VO over VI. So I'm multiplying top and bottom by VI. And I'm decomposing this. And the reason why I decomposed this was to then insert these terms I just derived. And here I have the gain. G sub V is the gain of the entire system. This is the gain of the amplifier, including the effects of R sig and RL. So let's think about this for a moment. If Rn is equal to, if R sig is equal to 0, if R sig is equal to 0, what does this equation turn into? What's that fraction turn into? 1, okay. If RL is equal to infinity, what does that equation, what does that fraction turn into? 1, okay? So if I don't have any RL or R sig, then VO is the global gain is just equal to AV0. So in this case, if I've got a 0 input resistance, or pardon me, a 0 signal resistance and an infinite load resistance, then this turns into 1, this turns into 1, and GV is just equal to AVO. But what if R sig is greater than 0 or RL is less than infinity? If that's the case, what do I know is going to be true about G sub V versus AVO? Same? Bigger? Smaller? It's going to be smaller, isn't it, right? This fraction becomes less than 1. That fraction becomes less than 1. So here's why we care about this. If R sig is greater than 0 or RL is less than infinity, then the global gain becomes less than the AVO, which is what the maximum gain the amplifier is capable of. Okay? Why is this true? Well, it's because of the effect of Rn and RO. If they weren't there, it wouldn't matter. If Rn was equal to 0, or if Rn was equal to infinity and RO was equal to 0, then it wouldn't matter what R sig and RL were, right? I would still get GV is equal to AVO. But because that's not true, because those are finite values in a real amplifier circuit, we find that our global gain is reduced. So why do we care about the input resistance and the output resistance? For exactly this reason. Because I can't guarantee that my input source is going to have a 0 resistance, a 0 input resistance on my signal source. It's not going to be an ideal voltage source. There's going to be some R sig value. I can't guarantee I'm going to connect always to an open circuit. There's going to be some load resistance. And unless I can build an ideal amplifier with infinite input resistance and 0 output resistance, which we can't do, then what we're going to find is connecting a load resistance and an input signal source absolutely impacts the value of the gain. And that equation describes how it works. That's why we care about Rn and Rout. Because as we're going to see, the input resistance and the output resistance will affect the overall gain equation. They will lower the effective gain that's possible because of those effects. So questions about this, what we just did here. All right? So like I said, I did all this to point out why we care about number 2 and number 3. And that's why you're going to be doing Thevenin equivalent circuits to calculate the input and output resistance, because it matters in an amplifier design what RN and RO are. It's going to impact your overall gain that you can get out of the amplifier. All right? Question? All right. So, having looked at this, let's now do some analysis of those amplifier topologies. We're going to do some small signal practice with these. Now, on these first initial topologies, guys, I'm going to kind of go through all the equations and kind of work them out explicitly. As we move on through the class, I'm not going to take time to write all the equations for the small signal diagrams. We're going to look at the small signal diagrams. We're going to talk about what they represent. But my assumption is going to be you guys can write those equations yourself, because it's nothing but nodal analysis. So the first few we'll do to see how it works, but after that, I expect you guys will be able to do all this on your own. That's, again, why it's so important. You need to be very confident in nodal analysis. You've got to be able to write those nodal equations. Okay, let's first talk about our common source amplifier. Again, we're just going to do this with NMOS, but I could do it with PMOS. So in this case, for my input signal source, I'm not going to assume an ideal input signal source. I'm going to assume that my input source, my AC source, has a Thevenin equivalent, has a voltage and a Thevenin equivalent resistance associated with it. And that's why now I'm going to put it into the circuit. So here's my common source amplifier in its most basic form. And I want to go through and calculate not only the gain, I also know what the input resistance is. I also want to know what the small signal output resistance is. So I want to calculate RN and RO. Obviously, those are going to matter to us. So in this case, I'm just going to transform this into a small signal diagram. What do? All DC sources go to 0. And then I substitute the small signal diagram of the NMOS transistor in place of that transistor, and I redraw the circuit. So notice what I've done here. I zeroed this out. All I've got left now is this connected to ground, which I just drew. That's my gate. This is my drain. And my source is ground. Source is grounded. And so I've got GM, VGS, and R sub O. These are the elements of my transistor for my small signal model. And then finally, I've got my R sub D, my drain resistor, which is connected from the drain also to AC ground, because VDD goes to 0. All right? So in this case, we actually did this circuit last week, right? We actually went ahead and analyzed this. So in this case, the difference between this week and last week was that resistor. But let me ask you guys a question. What's the small signal AC current flowing through that resistor from that diagram? 0, yeah, it's an open circuit, right? The gate's an open circuit. So this is 0, which means I have 0 volts across R sig. And so this is V sig, and therefore over here is also V sig. So what do I know about VGS and V sig? They're the same voltage. So by inspection, the signal source, the signal voltage, and VGS must be the same. Therefore, this GM VGS becomes GM times V sig. And now I'm going to write a KCL equation at the drain node. And what I get is that VO divided by, well, RO in parallel with RD. I can combine those two resistors together. So this plus GM times V sig is equal to 0, or VO over V sig is equal to minus GM times RO in parallel with R sub D. What is the input resistance of this? Okay. What's Rn seen looking into there? What's that going to be? Infinity, yeah, right? It's an open circuit. So Rn is infinity for this particular topology. What is the output resistance? Okay. Well, in this case, I'm looking back into here, so I'm going to be looking at R sub O, seen looking back into that amplifier. So I'm going to have to use the source driving technique because I have dependent sources. What do? Well, I set this equal to 0. All independent sources in the circuit go to 0. If that goes to 0, what happens to that dependent current source? Also goes to 0. And therefore, what is my output resistance going to be equal to? RO in parallel with R sub D. So it's equal to R sub D in parallel with R sub O. And we note, assuming that R sub D is much smaller than R sub O, little r sub O, which is generally going to be true, since that normally is true, R sub O for a transistor is usually going to be tens or hundreds of kiloohms. Then what we find is then the output resistance of the amplifier is generally just going to be approximately equal to the drain resistance. That's what you're going to find. Typically, the drain resistance dominates because it's so much smaller than this R sub O, the drain source resistance of the transistor. Okay? So the output resistance is typically going to be on the order of, anywhere in the kiloohms region. So typically, if it's dominated by the drain resistance, the drain resistor R sub D, it's typically going to be like a kilo ohm to 100 kilo ohms, something in that range. It's kind of typical values you see for most MOSFET amplifiers. The gain itself, this V over V sig, that's our AVO, our unloaded gain for the amplifier with no load resistance. And typically this is going to be a moderate to high value. And when I say moderate to high, I mean typically it's going to be on the order of maybe, maybe 10 to 100 type of values, okay? It can be less than that. I mean, you can design one with only a gain of 2 or 3. But typical amplifier gains are going to be moderate, 10 to 100 type values, maybe in the 10s to 100s. All right? It's all a matter of choices of the values, okay? Where you bias it and the components you use. All right? Notice the minus sign. This is an inverting amplifier topology. So the common source amplifier is an inverting amplifier, as we saw before, because of that minus sign. Now, looking at this, let's ask a question. What if I do this? What happens if we add a load resistor to the output? I'm going to call this R sub L. I'm going to assume that that capacitor C is large. It's big enough such that we can neglect the impedance at any AC frequency we care about. So this will be a large resistor. So the total impedance of this will effectively be dominated by R sub L. And this is the kind of assumption we're normally going to make. All right? If we do this, first of all, what does that capacitor do? Well, at AC, it's a short circuit. So in this case, Z is equal to effectively 0 at AC. We make the capacitance large. But what's it going to behave like at DC? DC, it's an open circuit. Is adding that capacitor and this load resistor going to change the bias point of that amplifier? No. The drain current will be, in other words, this is DC, when you're doing the DC analysis, this is disconnected. So the bias calculations remain exactly the same. But in the AC domain, what happens? Because of that capacitor, suddenly that resistor appears. So what do I get? Now I get this. I'm going to have a drain resistance in parallel with a load resistance now connected at that drain node. So in this case, what we get therefore what we get is VO over V sig is now going to be equal to minus GM times R sub O in parallel with R sub D in parallel with R sub L, which will be approximately equal to minus G sub M times R sub D in parallel with R sub L if R sub O is large. So if the drain source resistance of the transistor is large. So let me ask you a question. Did the magnitude of the gain go up or down when I added that load resistor compared to my original circuit? It went down. It decreased. Now, instead of RD, I've got RD in parallel with RL. So now the gain's decreased, and therefore the gain has been reduced. Loading effect. I loaded the amplifier, the gain went down. That's why we care. And it's going to be a function of the value of R sub D, right? What that's going to be. All right, so first circuit, common source amplifier. You guys see how this works. Next time we'll very quickly look at the common gate and the common drain amplifier circuits. Same type of analysis. We're going to see how they work. And then once we're done with that, we're going to move on to BJTs. And here's the nice thing about BJTs, guys. The small signal diagram is almost identical except with the addition of an additional resistor. If you understand these topologies, then the BJT stuff will be very obvious. All right? See you guys on Thursday.